Okay, hello, and thank you all for having me here. I drove over last night from Ohio. I work at the plant in Uricksville, Ohio. I'll show you a couple slides of, if I can get this. Yeah, let me do it here, okay. It's a picture of our factory. It was built in 1914. It's been in continuous operation. Since then, I've been there, actually I'm working on my 46th year there. A little bit of who we are: we mine our own clay. In fact, I take care of the raw material. That's an old picture. That's my old pickup truck there. So I still monitor and I take care of the raw material. This is the clay seam, and you can see a cool seam up above the cool. And so we do, this is a little bit new to me too, so let me wasn't expecting quite each slide coming through like this. Okay, that's good. We manufacture all the product at site, all the way from the raw materials, as you see. And I mentioned as I take care of the raw materials, the other job that I do, and there's some handouts out in the back there, as I work on AutoCAD. I've been working in designing fireplaces since the early 80s. So I'm going to talk about fireplaces, but we do also chimney tops, wall coping, line tile, bake ovens, and architectural terracotta. That's all our stuff here. And I actually brought a piece of custom architectural terracotta that we did on the Basilica here in town. It's a piece of green wall coping, but we did some real decorative finials on that project also. We're going to keep our subject to site-built masonry fireplaces. I do a lot of education. I actually do work with the New England Building Officials Association, and I go up there and do, usually on a smaller scale. I'm not used to talking to this many people. I do a lot of programs in offices, so I'm usually talking to a half a dozen or a dozen people. The same way with the Masons training. As you can see, here I am with half a dozen instructors, masonry instructors. So this is our design service, and this is the kind of drawings that I would do for specific projects. These are actually up in Wisconsin, a couple 72-inch fireplaces, and this is an outdoor fireplace. We offer the design service at no cost. This whole training program, if you want to review it, we're going to do a 1-hour fly through this. There's a lot of information on site-built masonry fireplaces that are covered in an hour. It's kind of tough to do. I'll try to pick pieces that I think that, being that this group is building inspectors, I'll try to spend a little bit more time and get to those, because sometimes I don't get to a lot of the details on building codes, because again, if I'm talking to designers, or if I'm talking to masons, I concentrate on different subjects. I brought all the product along here. Also, there's a folder here with some pictures of the actual factory and construction or manufacturing processes. And there's also a binder over here with architectural terracotta if anybody's interested in it. This whole workshop is on Rumford.com, so you can go in there and you can just go into detail as much as you want. Jim Buckley runs the Rumford.com site. Jim does a similar job as what I do. Jim's 86 years old. Jim's still very active, and I'm the younger 65-year-old version of Jim. So Jim will answer any questions. He's got a lot of blogs on there on, site-built masonry fireplaces. I'm going to spend a lot of time talking about a style called Rumford design, and I'll explain that. But I mean, all the things the code issues I'm talking about pertain to site-built masonry fireplaces, even though I'm going to talk about a specific style, and I have a lot of the components over here to my left. First and foremost, I want you to go away with the understanding of important safety and code issues that pertain to the design and construction of site-built masonry fireplaces. Second, I want you to have a better understanding of what makes a fireplace work and some of the basic physics that are at work in a masonry fireplace. And this has become very important as houses have tightened up. And we could probably talk on this subject for hours, and I gladly will spend an hour with you if you ever need an explanation or anything of what's going on in the structures. I spend a lot of time, a lot of my hours troubleshooting existing fireplaces, troubleshooting even new construction. You know, a lot of times or most times anymore, the HVAC people and the general contractors kind of put the fireplace on the side and they kind of forget about it. So a lot of times, even in new construction, we're going back after the fact and getting the fireplace to work. If we do it proactively, we won't have to do that, but it's a tough call. I mean, there's a lot of physics that's going on in a fireplace, and there's a lot of physics going on in a house. And again, in the next couple slides, I will explain that air requirements. To understand, we'll discuss, better measures that can be taken that are beyond the code requirements to improve the overall performance of the fireplace and masonry chimney system. Understanding and improving the energy efficiency of the fireplace, as well as the overall air quality of the home and the environment, relatively speaking. We are burning we're burning an active fire in a house, so there are some environmental issues both in the house that we have to consider, and putting the pollutants up in the air, that we want to keep them to a minimum. But in doing this, we can make the site-built wood-burning fireplace an attractive amenity. People want them. They just want them. They got to work. They got to be as efficient as possible. To better understand good fireplace design, we need a brief history of the fireplace design in the United States. So I've broken it down into 4 or 5 different segments or portions of history. The early American, this is prior to 1820. Wood was a major source of fuel. About 1840, coal became a major source of fuel. And again, not that we're going to go back to heating houses with wood, but if we're going to build a masonry fireplace, we want to make it as efficient as possible, meaning we get as much heat out of it as possible. Just to give you an example, a pound of wood is about 6,500 BTUs of energy, where coal is about 12,000 BTUs per pound of coal. So once coal became available, and that was in the Victorian period, and gas became, wood was not as important as a major source of heat. So the fireplace design sort of took a different direction. The Victorian period houses, this is mainly prior to central heating. So in a Victorian home, you would see probably a lot of times a half a dozen of these small, some of them were Rumfordish in design. Most of them were never intended to burn wood. Most of them at the beginning were intended to burn coal. So they had little grates in them, and then later on they were switched to the gas design. In fact, this is still a pretty large part or part of our business or industry is repairing these and replacing these. I've done many projects that, somebody will buy a house and it has 6, 8 Victorian fireplaces in it, and they either want to get them up and running, or most generally when I'm involved, they're replacing them with a real site-built masonry fireplaces. So there's almost a whole market in older towns like St. Louis. I'm sure there is. I'm not familiar with doing any projects. I've done quite a few projects in the Richmond, Virginia area, Charlottesville, places they'll buy these Victorian homes and then they'll put several $1 million in them, and they want the fireplaces to work. So that's, and actually in the handouts of my drawings, I've got assorted drawings that I've kind of pulled together that I feel are important drawings. I've got a couple sheets on Rumfordizing existing fireplaces, and I know for a fact one of them is a Victorian fireplace. By the 1920s, central heating was common, gas was cheap, but it's still prior to building codes. So the fireplace at this time period was really, I see a lot of different styles and very, very regional. And again, I work mainly from Texas to Minnesota to Maine down to Florida is where, seems like most of my design of fireplaces is. We do a lot in Colorado, as it seems like in the mountains of Montana. Other than that, those are the areas that fireplaces are still popular is Midwest and Northeast, with the exception again of Texas. They do a lot of fireplaces. So I see a lot of different. I see a lot of, quite honestly, dangerous things that was done back in this time period. They put a lot of, they would put wood close to the smoke chambers and close to the firebox. And again, this was because it was prior to building codes. And gas was cheap, and central heat was common in all central heating systems. So they really weren't concerned with the efficiency of the fireplace. It'd been 70 years since fireplace was a major source of heat. So, we lost a lot of the skilled or the good design masonry fireplace of the early 1800s when they were using them for heat. Post-World War II, it was a product of the time, and this is where fireplaces honestly got very inefficient. We're at probably 10 to 30% efficiency on fireplaces, meaning of how much wood you put into it. We can calculate all that. Say we put in 70 pounds of wood, and that might be 300,000 BTUs potential. It's not burning all at once, obviously, but if we're only getting 10 to 30% out of the fireplace, and this is what kind of turned people away from fireplaces, was these design fireplaces of the 50s, 60s, 70s, and in the 80s it even got kind of worse because the metal fireplaces came along, and any skill or talent of site-built masonry fireplace, it just really went to the wayside. Not to say that there wasn't some good fireplace designs and built in the 60s, 70s, and 80s, but it really got, and most of you will agree with me, at about the 1980s or so, it got to the point where you couldn't even find a mason to build a fireplace, and that's where we came along. Before that, we were just a manufacturer of clay flue lining. We seen that the clay flue lining industry was taking a hurt because there wasn't skilled masons coming up. So, and now that's already been a generation. We decided we worked with Jim Buckley and reintroduced the world to the Rumford design. This post-World War II, the fireplace I was talking about, that's what's called the common fireplace, the modern fireplace, conventional fireplace. That's one a lot of you are probably familiar with, and I'll explain the difference between a Rumford and a conventional fireplace. This leads us to the 21st century. Energy efficiency is a big concern. Emissions is a big issue. So, and architectural styles have changed. So these are some of the fireplaces that I personally have worked with or worked on, and these are all large fireplaces. And the reason I put them in there are they look conventional. They can be very conventional, modern style fireplaces. The one on my right there, you guys right too, that's the largest fireplace I've ever worked on. That's 18 foot of fireplace, and there's a wood-burning fireplaces. That's in Whistler Resort in British Columbia, Canada, and they're all natural draft. Everything we do, there's me and another designer that work at the plant. I've been here 46 years, and Mike Seibold's the other one that works is our CAD designer. He's been there 35 years. So we both are still working on a lot of fireplaces. To explain a little bit about Rumford design, it's named after Count Rumford. He was born in Benjamin Thompson in Woburn, Massachusetts in 1753, but he left. He was a loyalist. He went to Britain. He actually went to Bulgaria is where he went, and he did work with the nature of heat. And this is actually one of his drawings. So he took these fireplaces in these castles and chateaus that were real inefficient and didn't do a good job heating, so people were sick all the time because the air in the castles and chateaus were damp and cold. And he basically added the throat. The most important thing he did is this curved throat, and he made the firebox narrow, shallower and narrower. The side covings are at a 45-degree angle, so it reflects the heat into the room. The main thing he did without even realizing what he did, and it only has become real pronounced on houses that are very tight, is he created this airfoil here, this Venturi nozzle that squeezes the air together. It's like taking a water hose and squeezing, because air is a fluid, so it acts like fluid, and most of the, pretty much all the engineering that goes into fluid mechanics is used on pneumatic. That's what we're dealing with, is pneumatics, but it's fluid, so things flow. So is what you're taking is squeezing the air and assisting it up the chimney, reducing negative areas of air pressure. That's one of the things that's really come important in my study of fireplaces and designs. I've noticed as houses tighten up, anywhere we can reduce negative areas of air pressure in the fireplace, it takes less pressure to push or pull the fire. It's actually pulling the exhaust up the chimney. And I'll explain, because of the air pressure at the top of the chimney is less than it is at the bottom of the chimney. That's what creates the draft. And then when we add a fire to it, which is adding more pressure, it really is almost impossible for the fireplace not to work. It takes either a restriction or a negative air pressure to stop the air from going up the chimney. And once we realize that, as we're troubleshooting, if troubleshooting is required, we look at those two subjects and we'll figure it out. He wrote this essay in 1796, and the reason I've got it up there because I think it's a very important thing is what Count Rumford wrote was, his essay was on fireplace chimneys with the proposal to improve them to save fuel and render houses, dwellings more comfortable and salubrious, and effectively prevent chimneys from smoking. This is 1796, this guy wrote this. And salubrious is favorable to promoting health and being healthful. Nobody really did any design work or any writings. A guy named Vest Orton in 1969, and a lot of people know Vest Orton and will quote Vest Orton. Vest Orton was a hardware dealer up in New England, and he wrote a book on, he calls it, it's a Norton Rumford. It's pretty drastically different than a true Rumford. But that is what's called a Orton Rumford. This would be called a Count Rumford. Rumford design, just a few things on how a fireplace works. And again, air's flowing through this room. We're squeezing it together, adding energy, and pushing it up the chimney. This is a conventional fireplace. We hang this lintel down in front of the damper, which creates a area right here of turbulence. And again, that's negative air pressure, and it takes more positive air pressure to pull air out of negative areas of air pressure. A Rumford design fireplace, it virtually has no areas of negative air pressure, and that's why it drafts a little better on less air pressure. We can, by keeping the back wall straight and rounding the breast, we get streamlined airflow instead of turbulence. We can build the Rumford fireplace opening almost a foot taller than the regular fireplace, and the throat section is less than half. Sometimes it's only 1/3 of the fireplace opening. I'll show you in these. This is a conventional fireplace on the top. The throat opening's at the front, and it would be 36 by 10, which is 360 square inches. On the Rumford design, we put the throat opening. Rumford wouldn't have had a damper. The only purpose of the damper is to shut the air off when you're not using the fireplace, so you're not sucking cold air in the summer out, air conditioned, and you're not sucking warm air out in the winter when you're not using the fireplace. So we get this around 67 square inches. This takes about 360 square inches, and that's where a lot of our efficiency comes from. We reduce drag and the airflow, therefore we can move the same amount of exhaust of the firebox through a throat opening, almost 1/10 of the fireplace opening. It is pretty phenomenal. And this guy designed this without computers back in the day. Rumford Designs test, and when I keep saying Rumford, that's not a proprietary term. That's a style of fireplace, just so you know everybody understands what I'm meaning. I've got our Rumford style throats, but it doesn't need to be that. Guys do even built those in the field. Meaning for every 100,000 BTUs of wood that you put or you consume, you're getting 50 to 67,000 BTUs back out. This is compared to conventional design fireplace, which is about 10 to 30%. And I'm going to look at my phone one more time just to see what time I have. It's hard to get through this subject, all this subject matter, and there's certain things that I do want to get to. This is a very important thing here. I can explain a lot with this chart. This has to do with emissions, but it also has to do with how a fireplace burns. And once you can understand how the fireplace burns, everything kind of comes together. And this is a test that we've done numerous times. We actually have a third party do that. They're out in Arizona. We've had them tested up in Oregon because these are states where emissions is a lot bigger issue. States where we have higher elevation, and states that inversion is a big deal. When you get between two mountains and the hot air gets trapped in between the mountain ranges with cold air coming over top of it. We get inversions in our cities here during the summer when cold front comes in, and then it traps the pollution, smog down in the city. Well, in the mountains, they get it at odd times of the year. You never know when it's going to be, and they actually have no burn days on those days. So what we had to do as an industry, we're really stood alone on this because there's just the fireplace industry, masonry fireplace industry is very unorganized. It's a bunch of masons in towns all over the place, so they don't have the power to really do tests. And each time we do this test, it's $250,000. I think we've tested 3 times in the last 20 years. So obviously an individual mason doesn't have the capacity to do that. We as an industry, the flue manufacturers, now there's only 3 of us left, believe it or not. Manufactured in the United States, we're all in Ohio. We're there because of the clay. But we've done this testing. And what this testing, these are thermocouples. The black horizontal lines are thermocouples measuring temperatures at different areas of the fireplace without assisting draft, which is blowing on the fire bellows or something like that. Right here at the end in the fire, it's hard to get more than 1,400 degrees. Right above there where the other thermocouple, very similar to that, 1,000 to 1,100 degrees. The phenomenal thing about this, and Rumford would had no way of testing this, but these are thermocouples right at the top of the throat opening. We're looking at a vertical section, so the fire's here. Going up the back wall as TP style, we preach teaching it, burning it TP style versus laying down. It burns a lot more efficient. The fuel burns a lot more efficient, TP style. In our opinion, I think it even looks better, but it also keeps the gases more laminar, so they don't separate. And that's what this throat does. Well, this thermocouple right here, 1/2 inch from the front wall or front opening, never got above 150 degrees. All this test data is actually online if you go to rumford.com. 75 to 100 degrees. The thermocouple in the back, which is a 1/2 inch from the back wall, it would run 750 to 950 degrees. So what that tells us is that the air is laminar. It's not mixing, which is great for emissions, because the longer you can keep the gas above 650 degrees, the soot in the gas burns up, and this makes it cleaner burning. And this is what we had to do, or what we've done several times to meet the EPA standards. There is no EPA standard for fireplaces, so we have to meet the standard for wood burning stoves. So in these areas where it's not conducive to building masonry fireplaces, they want something that they can test and show the emissions. We have the test data, we have the forms. So in all these areas of the country, we have different counties that have different forms. And again, if you go to rumford.com, you can pick the state, you can pick the county, and we'll have the necessary forms to show that the fireplace meets the EPA standards. It works very similar to a catalytic converter. In fact, we even have experimented with putting catalytic materials on the back of the fireplace or up in the smoke chamber. The problem with catalytic materials is they work fine when they're real hot, but when they cool down, then they actually clog up and make the fireplace not work. So we're not to the point that we can put catalytic materials in. People do experiment with it, and with mixed luck. Most of the time it's not good luck, because it works real well when the fire's hot, but once the fire cools down, then the catalytic material clogs up. Dampers aren't as big of an issue as they were. It seemed like a few years back. The Energy Conservation Code was giving us a hard time about the dampers. They wanted us to use glass doors and supply all the air in the firebox, and that didn't work out too well, because you had to have ceramic glass, because regular glass would shatter with the heats that are in the fireplace. So we do have a gasketed damper. We are allowed to not exceed 20 CFM, and actually a regular Vestal dome damper does the same thing. It will still meet the EPA or the code requirements of not leaking more than 20 CFM. But that's what the gasketed damper looks like. I've got one over here. The other dome dampers, they actually, Vestal, there's only 2 or 3 manufacturers left that still, they do have a gasket. For a while, we were applying gaskets to their dampers because they didn't do it, but they will do it now. Design issues, so that, there's information out in the back there, or again, if you need any of this, it's online. I'm not going to run through a bunch of calculations and stuff for fireplace design. It's fairly simple, the calculations for flue size. I say size in the chimney pots and flues. The size of the chimney pot actually can be about 1/2 the size of the flue, and that's because the flue gas cools down by the time it gets to the top of the chimney. So there is actually an advantage to having a chimney top where you squeeze it back together, the air together, and assist it to create more velocity. But the flue size, and again, I've taken it out of the program because I don't have time to do it, but just for the sake of argument, or so that you understand, if you don't already understand, the flues are designated by the ASTM, the American Standard Testing Materials. Square and rectangular flues are the outside dimensions. So, for instance, a 12 by 12 is not 144 square inches. It's the inside dimension, which turns out to be about 10 1/4 by 10 1/4. Then you subtract the corners. Back in the day when I started pencil drawing, you actually had to do the tangents and subtract it. Now, after CAD came along, we draw it and we point and say, what's the square inches of that area? And so this is a flue chart, and there's nothing proprietary about this. You can find it in a lot of different places. It's actually in our catalog. It does the math for you. So if you had a fireplace, I'll just run real quick on it, and I don't have the slides that I used to. One other thing that plays a major factor in is the height of the chimney. And the reason this is the principles of the fireplace, the physics of the fireplace is why it drafts and why it draws, is the air pressure here is X, and the air pressure up there, 10 feet above the room, is about 3 pascals different. And a pascal is about the pressure of that you feel like right there. So that from here to there, it's about 3 pascals. If we put and go up 20, 30 feet, now all of a sudden we're probably 12 to 15 pascals of pressure different just in the air pressure from here to the outside, and the atmospheric pressure. And I'll show you a fancy formula for figuring all this, although that's not really necessary, but I will, and it's in your slide or in your presentation there. It's really not necessary. I just want to show it to you so you understand what's going on, because the atmospheric pressure here and the atmospheric outside does make a difference on the draft of the fireplace. But the basic physics is that there's less pressure the higher up you go on the earth, so it creates more suction, more draft. I like to use the example when I'm teaching high school students, and I usually have a lot more time, so I can do a lot more sort of experimentation. I'll take a water bottle, put some water in, put a straw in it, put it down in it, and blow across the top of the straw, and they get an understanding, which we should all get an understanding, that you're reducing the air pressure in the straw just as you would be if you put your mouth on it and suck on it. But when you do that, it gives it more graphic, and you'll see the water move up the straw. So that's the basic principles of the fireplace. So that's why when we have a fireplace that's 30 feet tall, and one of the largest houses I ever worked on, it was here in Springfield, Missouri, had 77-foot tall chimneys in it, believe it or not. And it was from the basement to the top. And it had fireplaces in the basement, first floor, second floor, and some on the third floor. So the fireplace at the bottom could use a smaller flue. In fact, we want to put a smaller flue. Back in the day, before houses, when they leaked, it wasn't as big a deal. But now, especially on any fireplace over 42 inches, it's very critical to get the flue right, because what happens in a house, as the fire dies down, it doesn't have as much pressure pushing the fire up or the exhaust up the chimney. So a smaller flue, it works better than an oversized flue in a bigger fireplace is a nightmare. I get these 72-inch fireplaces, and they work real well when they have a nice big fire. But when they go to bed at night, if they don't extinguish a fire or have glass doors to put on the door, it's almost guaranteed that big fireplace with that's going to have a 24 by 24 flue on it. And some of them I have, we'll do 24 by 36 flues. So, they can be a really big flue, a lot of area, so that it takes some pressure to push that up the chimney. It really only takes about 7 pascals of pressure to start to create a draft. So just as I said, if we're up 20 feet, 15 feet, we're going to have probably 7 to 10 pascals of pressure. And that's why most of our formulas, when we say 1/10, I don't know if you've all heard that, it's 1/10 of the fireplace opening is what the flue size should be. So let's do a real easy one. Is a 30-inch by 30 inches, 900 square inches. 1/10 of that is moving the decimal point. So we need 90 square inches for a chimney that's 17 foot tall. And we would go over here and we'd find 90. There's 102 is a 12 by 12 flue. Bingo, that's the flue we need for 900 square inch fireplaces. So it's not a real big deal. Anything 30 inch, 36, 42, the flue sizes are very manageable. 42 is a 13 by 18, very common flue. But when we start to get to 48 inch, and then we're at a 16 by 20 flue, it's a bigger flue, 18 by 18, and we get to the 60 inch, and then all of a sudden we're at 20 by 20 flues. Those are big flues. There's a lot of square inches. There's 300 square inches, so it takes a fair amount of pressure to push that up the chimney. In terms of CFM, it takes about 1 CFM for every square inch of flue area. So if we have a 20 by 20 flue that's 300 CFM, or 300 square inches, that's 300 CFM that we have to make sure that the HVAC guys taken in consideration, and the whole design team's taken that into consideration. And I can tell you, and maybe I don't know how many of you are architects in practice, but I can tell you 90% of the people are not going to take that into consideration. And that's where, you know, I'm constantly sort of driving that home to either the HVAC people are calling me or the architects are calling me, because I got plenty of documentation to back this up, to give them what they need. But to get back to the height of the chimney, if I have a fireplace that's going to require a 20 by 20 flue, which is 300 CFM minimum. If we had a real big fire, it might be 600 or 900 CFM, believe it or not. That's a lot of air. It takes more than this little 6 square inch opening that the code requires. That's what, and I'll show you what 6 inches, 6 square inches looks like in yeah, I'll show you that. But get back my point on the height of the chimney. If we had a 30-foot chimney and we had a 20 by 20 flue, we could probably get that down to a 13 by 18 probably. So a 13 by 18 is 173 square inches. Now that's 173 CFM. That's a huge difference between 300 CFM. This is the formula, and it's in there. I wouldn't bother a whole lot of time, but it's all relevant. It really is relevant. I try to, this next slide is a little bit more friendly. It's pressure difference, and these are all in that formula back there, is available pressure difference. And that's just what I talked about, you know, the ground here versus 10 feet, 20 foot, 30 foot, 40 foot, 45 foot, whatever it is, the pressure difference. The atmospheric pressure outside is somewhat plays into it, but really not as much as just the natural pressure difference between the floor level and the absolute outside temperature, absolute temperatures of the flue. These are all things that go into that formula. If you were to try to use that formula, I tell you the formula is not a waste of time, but it's not relevant or practical to use. It's more rule of thumb that we know work. But if you really wanted to figure out the reason is that formula that I showed you there. Balance in the ventilation system is very important. And I just talked about the calculations and assumptions for exterior requirement air. And this is all relevant. It's in the ESHRA handbook. Most honestly, it's very frustrating and how many times on really these high-end homes, you know, particularly if it's got a lot of fireplace. Like I said, I went to that one in Springfield, Missouri. Down in the Carolinas, the mountains of Carolina is just a huge market with big houses. So it's worth me running down there and working with these contractors. If it's somewhere I can go, I'll go and meet with the general contractors and the HVAC guys. I mean, many times I'll get really a hostile confrontation from the HVAC guys because they just refuse to work with a fireplace. And part of the reason is when they're things that they're doing in the HVAC are fixed, static things. You know, how many windows are in a structure, how many rooms you have, how many bathrooms you have. All this is kind of, this fireplace is not dynamic. It is dynamic. It's not static. It depends on how big a fire you have. But these things all can be figured out. If we know how many BTUs, we know how much combustion air that takes to produce those BTUs, turn that fuel into wood, that wood into fuel or energy. We can relatively guess how much air is being moved out of it. And there's actually, I have an apparatus. It's not real accurate, even though you would hope in the 21st century we would have some really nice things that we can hold up to that fireplace and it can tell me how much pressure or how many CFM or how much pascals. It's still just too dynamic. What's going on in the structure is very dynamic, and I will show you that. I want to get to it. This is what the code says. 6 square inches within 24 inches of the fireplace opening. That's in the IRC code. So this is 6 square inches. You know, that's probably twice the code. This is actually, that's the code right there, one of those. Code really doesn't make a distinction between a 30-inch fireplace and a 36 or 48 or 60-inch fireplace. This is called a combination ash dump. So the ashes go down the chute, and this goes to the outside. Very good system. These are all pictures that I've taken all over the country of different things. This is actually up in Rhode Island at a hotel. That's the air intake. They got cardboard in them. Regrettably, I've actually went to troubleshoot a project in Greenbrier, West Virginia. It's called the Sportsman Club. We put back-to-back 60-inch fireplaces. They put cardboard like that in the air intakes. Now, the air intakes weren't in the fireplace, but they didn't remove the air because they said when they took the cardboard out, without the fireplace going, the building was sucking in so much air that through that cold air return that was meant to be for the fireplace, people were getting cold, so they stuffed cardboard in it. So that tells you, that the structure needs air. I always compare it to a wood burning fireplace is the canary in the mine, meaning that when the air quality is not good, the canary died. Well, in this case, the fireplace smokes when the air quality is not right. This is some of the best examples right here. This is actually down in it's north of Little Rock. Joe Murdoch Masonry, he does a bunch of fireplaces with. Joe put this in there because I know Joe personally over the years. I've worked with him probably 20 years now. And I said, Joe, what's that all about? And he said, well, that's what the code requires. This is 6 square inches. This will supply a 30-inch fireplace. This is the actual air intakes. That's the air intake. That's what that fireplace needs. Now, it can be simply, all it's got to be is you reach down and you open a register, an outside register a dedicated duct that goes to the outside, or it can go to the crawl space, can't go to the garage, but it's got to be dedicated for this fireplace, because if not, you're going to steal the air, and that's what happens when they do put this in. A lot of times in a fireplace I went over in Pittsburgh with the HVAC guy where I got in the argument with him, he told me and I know this, every square inch of air that you take out of the structure, you have to replace. And then we start talking about the bathrooms, and the bathrooms, they don't put makeup. He didn't put makeup air for the bathrooms. And I said, well, then do you understand the concept that you're going to steal the air from what was meant to go to the fireplace? So I have no problem at all working with architects, engineers, and tell them how much air. And again, this is Joe Murdoch. He's the mason. He works with the general contractor to make sure that they have the air supply for this. I think this is I don't remember if this is an 84-inch fireplace. I did some 84-inch fireplaces with them, and I've done a bunch of big ones with them. This is air intake. These are air intakes. This is both the same house. This is a 60-inch fireplace. They had 2 of these, and this wasn't enough air. This was not enough air for this project. They brought more air in through a duct in the basement. It doesn't even have to be close to the fireplace. You just have to bring it into the system. It's like an empty water bottle, and that's the other experiment I'll show with young kids, is to take an empty water bottle and just suck the air out of it, and it just all collapses. A good analogy of this is even when you go up into the mountains of North Carolina or Pennsylvania, and you only have 1,000-foot elevation difference. If you have a water bottle, you can hear the water bottle creak, and if you got the lid on it. So those, and your ears pop, those are all pressure difference. The water bottle, you can take that and you can suck the air out of it, and it all crinkles, and if you poke a little hole, and that's what I'll do, I'll poke a little hole in the bottom of it, and you never empty it. You're just pulling the air through the water bottle, and that's what we have to do here. These, and again, I might get too many of these, but I think I can't get enough of them. Actually, this is an ugly one, but this is the air intake for this fireplace. These are the air intakes for this fireplace. This is a great idea, and I love it when a general contractor will have enough foresight to do this is that's a come on, yeah, that's in the wall. And actually, this is down in Lafayette, Louisiana. It's a funny story about this one is, this is about 10 years ago, and I went there when they were building it. They were putting 6 fireplaces in it, and I had work to do down in Texas anyway, so I stopped by the house, took that picture, and 10 years later, I get a call from the owner and the general contractor, met with all of them, and this exact fireplace was the only one that was giving them any trouble, and turned out that the wood wasn't, the wood was a little bit green, so it was creating more smoke and wasn't enough energy. But the bigger problem is there's a vent here and an outside vent right there, and this one was shut off. So it was as simple as I went out there, and within an hour we built a fire and didn't get it to smoke. And interesting story. Sometimes you can put the stuff in there if you don't follow through with it. Just as those air vents I showed you that Joe Murdoch puts in the floor there, sometimes you reach down and open a register, or you might go put a damper in the basement. So you got to go down and open the damper in the basement. Or I used to have slides of it. I took the slides out, but I had slides of a complicated over-the-top home in Connecticut. I think we had 12 fireplaces of that. And they actually had like a switchboard that it wasn't forced air, but it was just opening a damper. And they had a hole in the closet. They had a switch for each fireplace. So when they ran a fireplace, they would flip a switch and it would open a damper for that air intake to bring the air into the structure. A good example of how much air do you need, the house that I was talking about that I went out to Springfield, Missouri, had 18 fireplaces in it. I met with the masons, general contractor, HVAC guy, architect, and we were talking about air requirements, and we got to the subject of how much air, and I said, what's the parameters? The architect said, well, we have to, we want to figure on the worst case. What's the worst case? It's all 18 fireplaces are going at one time. Well, that's a physical impossibility, and it really took 200, I think it was 200, it was like the size of this elevator door is what it took. So they ended up breaking it down into 6 fireplaces. So if 6 of them were on, which was probably always the most practical, if you're even going to have 6 of them on at the same time, that then you would have so much air. And then if you had 12, you would have to have another system come on. Many times you can do it through the HVAC system. Get a lot of pushback from the HVAC industry. Because they don't want to pull that much outside air through the HVAC system with all their electronics and that, because they're pulling that much air, outside air. This is not air exchangers, because most of the time, first thing the HVAC guy will say is, we got air exchangers. I'm working on one up in Michigan. It's in a huge lodge. It's got 4-foot see-throughs in this structure. So it's got 2 on a big chimney chase on each side, and on each end of the building it has a see-through, 4-foot see-through that's open on both sides on the first floor, and then on our basement on the first floor it's got 2 8-foot or 4-foot fireplaces see-through, and they're having trouble with getting enough air. And his comment was the HVAC or the general contractor told me, we've got air exchangers. We even have at a cigar room that we have air exchangers. Well, I said, air exchangers is not what we're talking about. We're talking about makeup air. If you're just exchanging air, that's not what we want. We got to have positive air pressure in the structure. And nobody wants to hear that word. They don't want it to be positive. They want it to be neutral or sometimes negative. But we cannot have that if we're building a fire in the structure. It's as simple as that. I'll go to a structure the fireplace won't work, and they're just determined they're not going to bring outside air in. I flatly say that when you can't use that fireplace, and then obviously they change their mind and start thinking about how can I bring air in. You could bring air. I could bring air in over here and have the fireplace here, but when I bring the air in, it's going to come across the floor. So you have to think about how far away you go, and then what's in front of it. You put a couch in front of that, it's no good. One of the structures I went to that the homeowner 6 fireplaces in it, all worked except for the one without makeup air, because they said they refused to open the air in this. It was a 3-season room because it's Cleveland, Ohio, and it's 20 degrees outside or 20 below, and they're pulling cold air in. And I said, well, you know, on that 20 below zero day, you better not use that fireplace, because you have to have. And they already had the floor poured. They hadn't, like I said, they had makeup air, let's say over here, down low. I'm just showing it up here because you guys can't see it, but it has to be lower than the fireplace opening. That's code requirement. The air intake cannot be higher than the fireplace opening. So if we tried to bring air in up here and our fireplace is down here, if we pull hard enough, and we can calculate this in pascals, if we pulled hard enough, we can pull the air down across the room and in through this fireplace and up the chimney. But what happens as this fire dies down, doesn't have as much pascals, so it's pressure pushing up the chimney, and we have an air intake over here, which we're not allowed to do anyways. But if we did have one here, we run the risk of it will start pulling out that way. And that's why houses that leak, in the next slide we'll show that, when they leak, and if they leak up top, there are going to be problems with the fireplace. This is the old open the window, and that open the window is amazing how it works for calculating air requirements. Do it all the time. I have homeowners do it, so I don't even have to go to the structure. I say, you know, crack your window open. This is 24 inches. If this is 2 inches, and that's 48 square inches, that's what you need. This is a pneumatic air. So it's pneumatic. When the air becomes negative in the structure, this kicks on and pressurizes the room. Costs a lot of money and doesn't work. So that what happens is once the room's in negative air pressure, it's too late. You already got smoke in the room. You know, fireplaces and people are very, very sensitive to smoke in the room, in the fire. I mean, how many of you, I mean, will you go into a house and then nobody's burned a fire for weeks, and you go into the house and you smell wood burning fireplace? And that has nothing to do with the design of the fireplace. That's because the structure's in negative pressure and the fireplace is least resistance. So it's bringing air down your chimney. And that's all I have to usually do to convince the people. I said, well, explain how that's the fireplace is designed wrong. You're sucking air down your chimney when you're not even using the fireplace. So that tells you that there's problems in the house. It's real easy to fix. I can fix, like when you got the wood smell. I take an incense stick and I show the people, you know, here's smoke coming down open that window over there, quits coming down the chimney and goes up the chimney. That's because you know, it's like the water bottle. You've made that started bringing air in over there instead of bringing it down the chimney. So that's troubleshooting in a nutshell. And that's how it works. But it got where I want to get through this 5 minutes. The air, where it comes from, is very important on a tight structure. The stronger the wind on the outside, the more negative on this side. And this next slide will show you. If I was trying to bring air in through the air intake on this side of the structure, we're at 30 pascals on a windy day. And this is when somebody calls me and says, you know, something's wrong with the chimney. I only get smoke on a windy day. And I almost guarantee that it's never the air blowing down the chimney, it's being sucked down the chimney. And you could say, well, why does it happen on a windy day? I don't know if I don't have that slide anymore in here. I actually show what a negative side of the structure looks like. You're going to see leaves. I got a really, really good example at a house that on the back patio, the leaves are stacked all the way up against the house, and then the rest of the patio is all clean. Well, that's negative air pressure. Snow does the same thing. You know, it comes around. That's the negative side of the structure. If you try to suck the air from the negative side of the structure, it's not going to work, especially as this fire dies down and we don't have a lot of pressure going up the chimney. If we had a real good fire, we can create 45 pascals of pressure easily with a nice big roaring fire. So if we got 45 pascals of pressure going up the chimney, and on a windy day it's negative 30, we win the battle. But when the fire dies down, and now all of a sudden we may get as low as 12 pascals on a real, just a smoldering, smoky fire. We only got about 12 pascals, and we got 30. We're going to suck the air out. That's fine if we're going out. This is actually a safety hazard. We can actually suck the embers off you're not allowed to run this through wood framing. I've got a picture of it actually sucked the embers off the fireplace through the behind the fireplace into the wall cavity behind it and caused a fire. It didn't burn the place. Most of the time with site-built mason fireplaces, I could show you example after example. Most of the time the house doesn't burn down. It smokes before it burns, and people catch that and fix it. What causes fires and burns houses down are metal fireboxes with metal chimneys that run up through a wood chase, and that, because you don't catch it. But I mean, like I say, I could show you example of. I'm going to run out of time, but I just wanted one quick thing to explain is super negative attic spaces. We have the air running across the ridge vent. We're sucking the air out. If we're not bringing enough air in, and I've got a whole 2-hour slide presentation that I explain all that, we need to have this calculated right so that this is slightly in negative pressure, but we can't have it super negative, or we'll suck air out of the house. Troubleshot a house up in Connecticut. Turned out they had a 600 CFM fan up in the attic. Every time that attic fan would turn on, it would suck all the air out of the. Not only is it you're not going to build a fire successfully, it's unhealthy. I mean, I don't know if you have radon gas here. Ohio's terrible with radon gas. Usually when you got shale, and we got shale everywhere, is what we'll do is we can actually pull the radon gas through the wall because it's negative. I mean, you can pull, I've seen attics pull smoke into the attic through the concrete mortar joints. I'm out of time, and I know I got most things. One thing a code change. We have refractory mortar. It's not a code change, but it's something that people weren't aware of. The box should be put together with refractory mortar. I would like to talk about a change that is very important. We need 4 inches behind the firebox and 2 inches on the side. This is at the firebox. And we couldn't get them to budge on that because I actually went to the code hearings up in Rochester last year, 2 years ago. Couldn't get them to change that at the firebox, but at the chimney they did. They let us do this. At the chimney, we used to always have to be just 4 inches of masonry and then a 2-inch airspace. And it really didn't matter. They wouldn't even if we had 8 inches or 12 inches, they still wanted the airspace. This is like if we were going up through the second floor joist. Now, if we have 8 inches of masonry, we don't have to have any airspace around the flue. That's kind of huge for some design issue or design things that we're doing in a fireplace. Same thing. This got changed. This was 12 inches from here to the inside of the flue. Now it's 8 inches, and that's a new change. We need here is 2 inches of airspace right there beside the firebox. Here you can see it, and that's our throat. We do a smoke chamber, our system. It's actually some of my work there, but you have to have a brick between the flues. That gap between the flues can't be any greater than the thickness of the flue. That's code, okay? So this gap here, I might be pushing it there, but it can't be any greater than the thickness of the flue. This is a 13 by 13, so it can't be any greater than an inch. If we had a 24 by 24, we could have a 2-inch space there. We can't just run and I've seen people do it, run the flue up through the chase with nothing around it. This is just some stuff. If anybody's got any questions, this is some of my work, design work. If anybody's got any questions on any of our other products, please, like I said, I've been there 46 years. I've helped develop a lot of try to know as much as I can about refractory materials. We own Heat Stop, which is refractory concretes, refractory mortars, refractory insulated concretes. And I have some literature out there on the table on that Heat Stop. Firebrick, I've devoted all my working career to both developing these products and I still work with the raw materials. Wall coping's an interesting product. And we do architectural terracotta, although these are just plain red. I told you there's a green piece right here that came off the Basilica here in town. And we did a bunch of finials. I obviously didn't bring them along, but we did some big heavy pieces for that. And these are just some appreciate. I know I ran over of time, and anybody's got any questions, please. I'm here because I'm going to do a more hands-on one with masons later. And this is just some workshops I do all over the country. My day job is at the plant, but I mean I do a lot of this. I'm going to treat it sort of like a semi-retirement because I just turned 65, and so the workshops may way for me to get out of town.
Thank you so much.
Thank you.
That was fantastic. That was fantastic.
Well, thank you.
A lot of information. Will you do us one last favor and pick
Sure.
our business card drawing for the TMS? All right, we've got Joe Kovac, City of St. Louis. All right. Thank you all. We've got a full slate of seminars coming up between now and May. If you've got any questions, please stop by my office and ask me, send me an email. And we so appreciate you coming out today. Thank you. Oh, yeah. Do you already have a TMS? 2022?
No, I don't.
Well, then, there you go.
Thank you.
Yes?
Thank you, sir.